right, we are in section 1.3 and we're talking lines. So this should hopefully be mostly review. We might just put kind of some new terminology on some of these things that you should already be familiar with. So if we want to find the slope of a line between 2 points, x1, y1 and x2, y2, we have a formula to be able to do that. Typically, we think of this as being like rise over run. That's usually the expression that people talk about, where the rise is like the vertical change from point to point, and then the run is the horizontal change from point to point. When you look at these distances, the rise here, this length, it goes from a height of y1 to a height of y2. So if you want to find the difference, you just subtract. So we take y2 minus y1, like that. And then for the run, this distance, we're going from x1 right here to x2 right here. So to get that distance, again, we subtract. We take the difference. So that's going to be x2 minus x1. And now we just put these into this general formula for slope, rise over run. So that's y2 minus y1 over x2 minus x1. So this is what you would pretty traditionally see in a formula for slope. So for example, if we wanted to find the slope of the line containing the points 3, 5, and 6, 2, we would take y2 minus y1, right? So 2 minus 5 over x2 minus x1. 2 minus 5 is negative 3. 6 minus 3 is 3. And we would get negative 1 for our slope. So the line between these 2 points has a slope of negative 1. The question typically comes up, would it matter that I put this one first and this one second? No, not necessarily. You could switch the order around, and that would be fine as long as you're consistent. So like if this is y2, this one has to be x2. Or if this one was y2, then this one would have to be x2. So you can pick whichever point you want to go first, but you have to be consistent in which ones go together. So these two are the same point and these two are the same point. Now, when we talk about slope of a line and how it relates to functions, which we've been talking about in the last couple of sections, we kind of relabel these things a little bit. So we can compute what we call the average rate of change of a non-linear function, f of x, on an interval from a to b using the difference quotient. So I have a diagram here for us to look at, and I know there's a lot going on here, and we're going to talk through it. So we have a function f of x, and we're going from a to b. Okay. We know that at the value a, we plug it into the function, we get out f of a. At the value b, you plug that into the function, you get out f of b. We don't know what specific numbers these are because this is all very arbitrary, very general. But we have a goes with f of a, b goes with f of b, and I've drawn a line between these 2 points, and we're going to try to find the average rate of change between them by simply finding the slope of this line. Okay, so this average rate of change, you'll see I have a label on the line over here. This is also called the slope of the secant line. So a secant line is a line that crosses through a graph at 2 different points. So precisely like this one that I have here. So the slope of the secant line is also considered average rate of change. Okay, so this is the slope of the line between 2 points. So if we want to find average rate of change over this interval, we need to take, again, like rise over run. So the rise in this case, we're going from f of a to f of b. So we're going to have f of b minus f of a. So we're going to take the difference of those. And then same thing here, we're going from a to b. So we take the difference. We take b minus a. So we get f of b minus f of a over b minus a. And if you compare this with what we just did up above, they basically are the same formula, right? Because you have, instead of x1 and x2, you have a and b, which are both x values. Instead of y1 and y2, you have f of a and f of b, which are both y values, right? Output values. So it is the same formula, but because we're dealing with a function here that is not necessarily linear, we like to rewrite it using this notation. Just makes it a little bit easier when evaluating. Okay, so this is, again, average rate of change. This is change across this line from point A to point B. Obviously, the rate of change at any particular point is going to be different, but we're just looking, again, on average. The concept of the difference quotient, we're going to be talking about that a little bit more later on as well. But the difference quotient, so a difference is like subtraction, so like these, and a quotient is division, so this. So it's called a difference quotient because it has a quotient between two differences. So that's, where that name comes from. But let's take a look at an example. So if f of x is x squared minus 4, find the difference quotient, right, that average rate of change, and simplify. Then find the slope of the secant line from x equals 3 to x equals 6. So we need to evaluate this function at x1 and at x2. So these are going to be replacing the x's in here. So we're going to have x2 squared minus 4 minus x1 squared minus 4 all over x2 minus x1. So again, this is f of x2, this is f of x1. And now a lot of this just comes down to simplification. So we have x2 squared minus 4 minus x1 squared. Don't forget to distribute that negative, though. So we get a plus 4 over x2 minus x1. The 4's will cancel. So we have x2 squared minus x1 squared over x2 minus x1. Okay, if you remember some stuff about factoring, factoring is something that we can do when we have squares like this in some cases. In this case, this expression, we have subtraction between two perfect squares. This is called a difference of squares, if you remember that terminology. And that absolutely factors as x2 plus x1 times x2 minus x1. And this is all over x2 minus x1, like that. And now we have a case that is similar to what we saw in an example in the previous section, where individually these can't cancel like this because of the addition and subtraction. But this is now a multiplication problem, right? You have this whole expression times this whole expression. So we can take this whole expression and cancel it with this whole expression. So we just go like that. And that's just going to leave us with x2 plus x1, like that. So we got our difference quotient, and we simplified as much as possible. We got down to here, and now it's asking us to find the slope of the secant line from x equals 3 to x equals 6. Okay, so slope of the secant, that's m, equals f of 6 minus f of 3 over 6 minus 3. Okay, and we could go through this whole process again if we wanted to, right? You could just do, 6 squared minus 4 minus 3 squared minus 4 over 6 minus 3, etc., etc. But we already went through the whole process of finding the formula and simplifying it. So why don't we just use it, right? We got x2 plus x1. x2 is 6 plus x1 is 3. And that gives us 9. So we know that the slope of the secant line from 3 to 6 along this function is 9. Okay, so it's a very steep function. And this is a parabola, right? This is a graph that looks something like this. So to go from 3 to 6, it's going to be, something very, very steep as you draw that line. So this tracks with what we know about that function visually. But again, if we hadn't done any of this, you could absolutely still solve it like this and get out the 9. But we like having the general formula simplified first because now we can use this version of it anytime we want to go between two numbers for this function. So it can simplify, the repetition of having to solve multiple problems using the same f of x. Okay, but that is the slope of the secant line. So keeping in line with this idea of lines and linear functions, so a linear function can be put in the form y equals f of x equals mx plus b. Right, we're used to y equals mx plus b. That's the slope-intercept form of a line, right? Slope-intercept form of the line. But we often will rewrite it using f of x just to keep it as a function now that we're doing all things with functions, where m and b are real numbers, with m representing slope and b representing the y-intercept or the vertical intercept. So slope-intercept form is probably the most commonly used form of the equation of a line, but you can also write them in point-slope form if you know one of the points on the line, x1, y1, and that is y minus y1 equals m times x minus x1. So this is point-slope form. This is another perfectly valid version of a linear equation and perfectly equivalent to. So this version and this version are interchangeable. They both will give the same results. You can find one using the other. So it's all the same. But slope-intercept form is nice because we already know what m and b represent. So we don't have to plot points one by one. We can use what we know about slope and y-intercept. So, for example, graph the function, the linear function, f of x is negative 2/3 x plus 2. So we know that this is slope-intercept form. So this 2 is going to be the y-intercept. And then the slope is negative 2/3. So for the slope, This is, again, rise over run. So we're going to go down 2 and right 3 for our slope. So we're going to start at 2. We go down 2, right 3, down 2, right 3, down 2, right 3, etc. And I can kind of backtrack here just so that we have a more complete picture of the line. And this is what we're going to get. And my system should correct it. Perfect. Right, and I'll put little arrows on the ends because it does continue in both directions forever. But that would be the graph of this linear function. We can also take either a graph or just even 2 points that we know are on a line, and we can come up with the equation of that line from these points. So in this example, we have the point -2, 2 and 4, 1, and we want to find the equation of the line that passes through them. Now, the first thing we're going to find is the slope. So we know that to do this, we're going to take y2 minus y1 over x2 minus x1, right? So that's 1 minus 2 over 4 minus -2. So that's -1 over 6. And I particularly underlined and now highlighted this word because a lot of times people get kind of complacent, I suppose, and think like, oh, I found the slope of the line, I'm all done. And they forget that the question actually asked for the full equation of the line. So don't just stop at the slope. Make sure that you read the question, know what it's asking for, because those are the kinds of things that are easily fixable, but people sometimes are just in such a rush they don't realize that they didn't actually answer the question. So to find the equation now, we can use the slope and either one of the points. I'll go ahead and put it in point slope form. I'll use the first point, the -2, 2. So we'll get y minus 2 equals -1/6 times x minus -2. So this is point slope form. It's the one that was right back up here. And no, it doesn't matter which point you use. Both points will provide the same answer. So we get, let's see, minus -2. This is going to become a +2 right there. So we get -1/6 x minus 2 over 6, which is 1/3. So we get y equals -1/6 x. We're going to go ahead and add the 2 to both sides. So we're going to get 2 minus 1/3. So that's 1 2/3, which as an improper fraction is 5/3. And that would be the equation of this line. So this is our kind of introduction back into linear functions, into linear graphs. We looked at average rate of change, right? The slope of the secant, all of that kind of stuff. And this section really is kind of a transition point. We're going to start moving towards more calculus-based concepts starting in the next section. That's going to lead us throughout the rest of the chapter. We will be revisiting these concepts again in a couple of sections, but that is the end of section 1.3. So I will talk with you all in the next one.